Right now, the farthest human-made object ever launched is Voyager 1. It has been flying away from Earth for nearly 50 years at 38,000 miles per hour. It has never slowed down. It has never stopped. And after all that time, all that speed, all that distance, it has not even crossed 1% of the way to the nearest star. It is still inside our solar system. It will remain inside our solar system for another 30,000 years. And Voyager carries no crew, no life support, no return plan. It is an 1,800-pound machine running on the energy of a light bulb. What we are about to walk through is why the distance beyond our sun may not just be difficult. It may be the permanent outer boundary of human reach. If you find this kind of deep science fascinating, do me a small favor and hit the like button and subscribe. It genuinely helps this channel grow and lets us keep making content like this. Are you comfortable? Now, let's begin. There is a story humanity tells itself. It goes like this. We started on one planet. We looked up. We left the ground. We reached the moon. We sent machines to Mars. We flung probes past Jupiter, past Saturn, past Neptune, and into the black. Each step was harder than the last. Each step was taken anyway. And the next step, the one that sits glowing on the horizon of every science fiction novel and every space agency roadmap and every late-night conversation about the future of our species, is the stars. We will leave the solar system. We will reach another star. We will find another world. It feels inevitable. It feels like the natural continuation of a line that has only ever pointed in one direction. Outward, farther, more. That story is one of the most powerful narratives in human civilization. It has inspired generations of engineers, scientists, dreamers, and explorers. It has shaped how governments fund research, how cultures imagine the future, and how individuals understand their place in the universe. And it may be wrong. Not wrong in the way that a budget estimate is wrong, or a launch window is missed. Wrong in a deeper sense. Wrong in a way that most people have never seriously considered. Because the emotional momentum of the story is so strong that questioning it feels like giving up. But this is not about giving up. This is about seeing clearly. And what becomes visible, once you strip away the inspiration and look only at the physics, the engineering, the biology, and the math, is something that should change the way every person on Earth thinks about the future of human exploration. To understand why, we have to start with the assumption itself. Where did it come from? Why does it feel so certain? The answer is that humanity has had an extraordinary century. In 1961, Yuri Gagarin became the first human being to orbit Earth. 8 years later, Neil Armstrong and Buzz Aldrin walked on the moon. 8 years. From first orbit to lunar surface in less time than it takes to pay off a car. That pace set the expectation. If we could do that in 8 years, what could we do in 80? In 800? The trajectory seemed exponential. Every decade brought something new. Space stations, shuttle programs, rovers on Mars that sent back photographs so sharp you could see individual pebbles on the Martian surface, probes that visited every planet in the solar system, telescopes that peered 13 billion light-years into the past and photographed the afterglow of the universe's birth. The James Webb Space Telescope, launched in late 2021, is now studying the atmospheres of planets orbiting distant stars, looking for the chemical fingerprints of life. Each of these achievements was real, each was extraordinary, and each one cemented the belief that exploration is a line, and the line only goes forward. But here is what almost nobody pauses to consider. Every single one of those achievements happened inside the solar system. Every human being who has ever lived has lived inside the solar system. Every spacecraft that has ever returned data to Earth did so from inside the solar system. Every rescue, every repair, every course correction, Every improvised solution that saved a mission from failure happened within a domain where the sun's gravity still dominates, where communication with Earth is measured in minutes or hours, and where the basic architecture of support, return, and recovery still functions. The solar system is not a small place. It is staggeringly, almost incomprehensibly large. But it is a bounded place. And the boundary matters far more than most people realize. Ask someone where the solar system ends, and most will point vaguely past Pluto. Some will say Neptune, since it is the outermost planet. A few might mention the Kuiper Belt, the ring of icy objects beyond Neptune that stretches out to roughly 50 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. 50 astronomical units is far. It is roughly 4.6 billion miles. But the solar system does not end at the Kuiper Belt. It does not end at the heliopause, the boundary where the Sun's solar wind gives way to the pressure of interstellar space, located at roughly 123 astronomical units. It does not even end at the region where Voyager 1 currently flies, approximately 172 astronomical units from the Sun as of early 2026. The solar system, defined by the Sun's gravitational dominance, extends to the outer edge of the Oort Cloud. The Oort Cloud is a vast spherical shell of icy bodies that surrounds the entire solar system. Its inner edge begins at roughly 1,000 to 2,000 astronomical units from the Sun. Its outer edge is estimated to lie at approximately 100,000 astronomical units. Some estimates push that boundary even further, to 200,000 astronomical units. To put those numbers in terms that convey their meaning rather than just their size, 100,000 astronomical units is roughly 1.6 light-years. The Sun's gravitational domain reaches 1.6 light-years outward in every direction. The full span of the Oort Cloud, measured from one side to the other through the Sun, is over 3 light-years across. Over 3 light-years. That means a beam of light, traveling at the fastest speed anything in the universe can travel, takes more than 3 years to cross the space that our solar system occupies. That single fact should recalibrate everything that follows, because the nearest star system, Alpha Centauri, is approximately 4.37 light-years away. The gap between the outer edge of our solar system and the nearest star is nearly twice the distance from the Sun to that edge. The solar system is not a small pond at the edge of a vast ocean. It is already the ocean. And the distance between our ocean and the next one is a crossing that dwarfs anything inside it. This is where the story of Voyager 1 becomes essential. Not as an inspirational tale of human ingenuity, although it is that, but as a measuring instrument, a ruler laid against the void. Voyager 1 launched from Kennedy Space Center on September 5, 1977. It carried instruments to study Jupiter and Saturn. It completed those flybys brilliantly, returning images and data that transformed our understanding of the outer planets. After its encounter with Saturn in November 1980, the spacecraft was redirected on a trajectory that would carry it out of the plane of the planets, away from the Sun, and into the outer reaches of the solar system. It has been flying on that trajectory ever since. It has never stopped. It has never slowed down significantly. It is traveling at approximately 38,000 miles per hour, or roughly 17 kilometers per second. That is fast by any human standard. It is faster than a bullet. It is faster than any vehicle most people will ever encounter. And it is nowhere near fast enough. As of March 2026, Voyager 1 is approximately 172 astronomical units from the Sun. In November of 2026, it is projected to reach a milestone that NASA itself has highlighted. It will become the first human-made object to be 1 full light day from Earth. That means a radio signal traveling at the speed of light will take 24 hours to reach the spacecraft. A command sent on a Monday morning will not receive a response until Wednesday morning. That milestone is remarkable. It is also quietly devastating when you understand what it means in context. One light day is roughly 173 astronomical units. The inner edge of the Oort Cloud begins at roughly 1,000 astronomical units. Voyager 1 has not yet covered even 1/5 of the distance to the Oort Cloud's inner boundary. NASA estimates that it will take Voyager 1 approximately 300 years to reach the inner edge of the Oort Cloud, and roughly 30,000 years to pass through it and exit the other side. 30,000 years. For reference, 30,000 years ago, anatomically modern humans were painting on cave walls. Agriculture did not exist. Writing did not exist. The wheel had not been invented. The entirety of recorded human civilization, from the first Sumerian clay tablets to the device you are watching this on, fits inside a window of roughly 5,000 years. Voyager would need 6 times that span of history just to leave the solar system. And Voyager is not carrying a human crew. It has no life support, no food, no oxygen, no radiation shielding beyond its own structural materials. It is a spacecraft that weighs roughly 815 kilograms and runs on the decaying heat of plutonium-238, producing less electrical power than a standard household light bulb. As of 2026, only 2 of its scientific instruments remain operational. Its power supply is fading. Its thrusters are degrading. Engineers at the Jet Propulsion Laboratory describe the spacecraft as single string, meaning there are no backup systems remaining. Every component is the last one. If anything critical fails, the mission ends. And this is the fastest, most enduring, most successful deep space machine humanity has ever built. If Voyager is our best case, and it cannot exit the solar system for 30,000 years, the question of how a crewed mission would do it is not a question of optimism. It is a question of arithmetic. And the arithmetic does not cooperate. Here is the part of the story that almost never gets told clearly enough. The difference between interplanetary travel and interstellar travel is not a difference in degree. It is a difference in kind. These are not 2 points on the same scale. They are 2 completely separate categories of challenge, and treating them as a continuum is one of the most dangerous misconceptions in all of space exploration. Consider the distances. Mars, at its closest approach to Earth, is roughly 0.37 astronomical units away. That is about 34 million miles. Light covers that distance in roughly 3 minutes. A robotic signal, a course correction, a critical command can reach a spacecraft at Mars in minutes. A crew at Mars can talk to Earth with a delay that is annoying but manageable. A resupply mission, while expensive and difficult, is conceivable on a timescale of months. A return trajectory is well understood. We have sent dozens of missions to Mars successfully. It is far. It is hard. It is not impossible. Now consider Alpha Centauri, 4.37 light-years. That is approximately 277,000 astronomical units. To compare, Mars at closest approach is 0.37 astronomical units. Alpha Centauri is roughly 750,000 times farther away, not 750 times. 750,000 times. That factor does not just make the journey longer, it transforms every parameter of the mission into something qualitatively different from anything ever attempted. At Voyager 1's speed, roughly 17 kilometers per second, reaching Alpha Centauri would take approximately 73,000 years. Even at the speed of the Parker Solar Probe, at its closest approach to the Sun, which has reached velocities exceeding 190 kilometers per second, making it the fastest human-made object in history, the journey would still take roughly 6,700 years. Those are not engineering timelines. Those are geological timelines. They are longer than most civilizations last, longer than most languages survive. longer than most species, remain behaviorally stable. To cover the distance to even the nearest star in a human lifetime, a spacecraft would need to travel at a meaningful fraction of the speed of light: 5%, 10%, 20%. At 10% of light speed, roughly 30,000 kilometers per second, the trip to Alpha Centauri would take about 43 years. That is within a single human lifespan. It sounds almost reasonable until you ask what it takes to accelerate a spacecraft to 10% of the speed of light and keep it there. The energy requirements are beyond anything humanity has ever produced for a single purpose. Accelerating even a modest payload, say 10,000 kilograms, roughly the mass of a large crewed capsule without any of the life support, shielding, or supplies needed for a decades-long mission, to 10% of light speed requires energy on the order of magnitude of the total energy output of entire nations for years. The physics is not ambiguous. Kinetic energy scales with the square of velocity. Doubling the speed requires 4 times the energy. Reaching 10% of light speed does not require 10% of the energy needed to reach light speed. It requires 1% of that energy. And 1% of the energy required to accelerate a meaningful payload to light speed is still a number so large that no existing or plausibly near-future energy source can deliver it. Chemical rockets are ruled out entirely. They do not carry enough energy per unit mass. Their exhaust velocities are too low. You would need fuel loads so massive that the fuel itself becomes the dominant mass of the spacecraft, requiring even more fuel to accelerate the fuel in a cascading equation that spirals into impossibility long before you reach interstellar speeds. Ion drives are far more efficient in their use of propellant, but they produce thrust measured in millinewtons. They are excellent for slowly adjusting the orbits of satellites or gently accelerating a probe over years within the solar system. They cannot push a crewed vessel to interstellar velocities within any useful time frame. Nuclear thermal propulsion offers better performance than chemical rockets, but it is still fundamentally limited by the energy density of fission reactions. It could meaningfully shorten travel times to Mars. It cannot bridge the gap to another star. Nuclear pulse propulsion, the concept of detonating nuclear bombs behind a spacecraft and riding the shockwave, was studied seriously in the 1950s and 60s under Project Orion. It is one of the few propulsion concepts that could theoretically reach a small percentage of light speed. It was abandoned for reasons that included treaty obligations, the sheer scale of the required nuclear arsenal, and the engineering challenges of building a ship that could survive thousands of nuclear detonations at close range. Fusion propulsion, the idea of harnessing the same reaction that powers stars, remains the most promising theoretical path. But controlled fusion for power generation has not yet been achieved on Earth after more than 70 years of research and tens of billions of dollars of investment. Building a fusion engine compact enough and reliable enough to operate for decades aboard a spacecraft is a challenge that sits behind a challenge that we have not yet solved. The most ambitious propulsion concept ever seriously funded was Breakthrough Starshot. Announced in 2016 with the backing of physicist Stephen Hawking and investor Yuri Milner, it proposed using a ground-based laser array with a combined power output of 100 gigawatts to accelerate a gram-scale spacecraft attached to a light sail to 20% of light speed. At that velocity, the tiny probe could reach Alpha Centauri in roughly 20 years. The concept was elegant. It was also limited in ways that reveal the depth of the problem. The spacecraft would weigh roughly 1 gram. It would be a chip, not a crewed vessel, not even a traditional robotic probe. A chip with a camera, a power source, a communication laser, and a sail a few meters across and thinner than a human hair. It would fly past Alpha Centauri at 20% of light speed, unable to slow down, unable to enter orbit, capturing what images it could during a flyby lasting hours at most. The data it gathered would then take over 4 years to transmit back to Earth. By 2025, the project was reported to be on indefinite hold. It had spent approximately $4.5 million of its proposed $100 million budget. The engineering challenges, particularly in sail materials, beam stability, and the sheer cost of the laser array, estimated at around $8 billion for capital alone, had proven more formidable than initial optimism suggested. And this was the easy version. This was a chip, a gram of silicon, no crew, no life support, no return. If a gram-scale flyby mission strains the edge of human engineering and economics, the idea of sending human beings on a journey that requires them to survive for decades or centuries in deep space, at speeds we have no current way to achieve, protected by shielding we have not invented, supported by systems that have never been tested at that duration, communicating with a home planet that grows more distant and more silent with every passing year, is not the next step on a familiar staircase. It is a different staircase entirely, and we have not yet found the first step. And there is a dimension of this problem that the propulsion discussion alone does not capture, because it concerns not the journey, but the destination. Every number cited so far, every transit time, every energy calculation, every radiation estimate, is built on the assumption that Alpha Centauri, the nearest star system, is where an interstellar mission would go, 4.37 light-years. The closest possible target, the best case, the smallest conceivable crossing. But the question that almost no popular account of interstellar travel asks honestly is whether Alpha Centauri is actually worth going to. The Alpha Centauri system contains 3 stars. Alpha Centauri A and B are a binary pair, 2 stars orbiting each other at distances that range from roughly 11 to 36 astronomical units, roughly the distance between the Sun and Saturn at the close end, and the Sun and Pluto at the far end. The 3rd star, Proxima Centauri, is a small red dwarf orbiting the binary pair at a distance of roughly 13,000 astronomical units. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri in its habitable zone. Proxima Centauri b made headlines around the world. An Earth-sized planet in the habitable zone, orbiting the nearest star. The discovery felt like the first chapter of the story everyone had been waiting for. But the details that followed the headline were less encouraging. Proxima Centauri is a red dwarf flare star. It produces violent stellar flares that can increase its brightness by a factor of several hundred in minutes. These flares bombard any close-orbiting planet with intense ultraviolet and X-ray radiation at levels that would sterilize an unshielded surface and, over geological timescales, could strip away a planet's atmosphere entirely. Proxima b orbits its star at a distance of only roughly 0.05 astronomical units, far closer than Mercury orbits the Sun. At that proximity, the planet is almost certainly tidally locked, meaning one hemisphere faces the star in permanent day, while the other faces away in permanent night. The temperature differential between the 2 sides would drive extreme atmospheric circulation if an atmosphere exists at all. Whether Proxima b retains an atmosphere, whether that atmosphere contains water, whether the surface conditions permit anything recognizable as habitability, all of these remain open questions. The planet is not confirmed as habitable. It is confirmed as existing in a zone where liquid water is theoretically possible under specific atmospheric assumptions that may or may not hold. The distinction between those 2 statements is the difference between a destination and a hypothesis. The Alpha Centauri A and B binary pair presents different but equally challenging problems. The gravitational dynamics of 2 stars orbiting each other create zones of orbital instability that restrict where planets can maintain stable orbits. Planets orbiting too far from either individual star would be perturbed by the gravity of the other, their orbits destabilized over millions of years. Stable planetary orbits in binary systems are confined to relatively narrow regions, close to one star or the other, or very far from both. As of 2026, no confirmed terrestrial planet has been found orbiting Alpha Centauri A or B. There have been candidate detections, including a thermal signature reported by the James Webb Space Telescope near Alpha Centauri A, but follow-up observations have not confirmed a planet, and the detection remains ambiguous. The Alpha Centauri system may contain rocky worlds. It may not. The data does not yet tell us. What it does tell us is that the nearest star system is not a known destination with a confirmed habitable world waiting for arrival. It is a three-star system, with one candidate planet orbiting a flare star under conditions that may preclude habitability, and two other stars around which no Earth-like planet has been confirmed to exist. If Alpha Centauri turns out to be unsuitable, the next candidates are farther away, and each additional light-year multiplies the severity of every challenge this story describes. Barnard's star is approximately 6 light-years from Earth. It is another red dwarf, and its candidate planet, Barnard B, if it exists, orbits well outside the habitable zone in conditions far too cold for liquid water. Wolf 359 is roughly 7.9 light-years away. It is one of the faintest stars known, another red dwarf, with no confirmed planets as of this writing. Ross 128 is approximately 11 light-years away. Its planet, Ross 128b, is one of the more promising nearby candidates, orbiting a relatively quiet red dwarf in the habitable zone, but 11 light-years translates to a minimum transit time of roughly 110 years at 10% of light speed, a speed no crewed vessel can achieve. At more realistic velocities, the journey stretches into multiple centuries. Every number in this story has been calculated against the most optimistic possible distance. 4.37 light-years. The nearest star, the shortest crossing. If that crossing proves to lead nowhere habitable, the actual distance to a viable destination could be 2, 3, or 5 times greater. And every factor described in the story that follows, propulsion, communication, radiation, life support, system degradation, psychological endurance, scales with that distance. Not linearly. Exponentially. The destination problem does not replace the journey problem. It compounds it. The journey was already at the edge of possibility. If the destination is not where we hoped, the edge moves further away. This is the fracture point that the rest of this story will explore. The solar system is not a waiting room. It is not a training ground for something grander. It may be the grandest stage we ever stand on. Not because we lack ambition, not because we lack intelligence, but because beyond a certain threshold, the accumulated demands of distance, time, energy, exposure, and isolation may exceed what any human mission can sustain. Every challenge described above is real. Each one has been studied in detail by researchers at NASA, ESA, and universities around the world. Each one, taken alone, is severe but potentially addressable given enough time, funding, and ingenuity. Taken together, they form something different. They form a wall, and the wall is not made of one material. It is made of every material at once. Propulsion limits reinforce communication limits. Communication limits reinforce isolation. Isolation reinforces psychological strain. Psychological strain reinforces the fragility of the social and institutional structures needed to keep a multi-generational mission functioning. Radiation exposure compounds over the decades that inadequate propulsion forces the crew to spend in transit. Life support systems degrade over the same decades, while resupply becomes impossible and repair depends entirely on whatever was brought aboard at departure. Each problem feeds the others. Each shortfall makes the rest worse. The question is not whether any one of these challenges can be solved. The question is whether all of them can be solved at the same time, for the same mission, sustained across the same timescale, with no external support? That question has an honest answer, and the honest answer is that no one knows. But what the physics tells us so far is not encouraging. And the deeper we look at each link in the chain, the more clearly we see that this is not a challenge of building a faster rocket. It is a challenge that reaches into the deepest foundations of what human exploration actually requires, and asks whether those requirements can survive the crossing from one star's domain to another. What comes next will break this down link by link. Propulsion, communication, radiation, life support, system failure, continuity, not in isolation, but in combination, because it is the combination that defines the real boundary. And what that boundary looks like, once you see it clearly, may change the way you understand not just space travel, but the future of the species that dreams about it. Every engineering problem in the history of human spaceflight has shared one quiet advantage. The sun was nearby. Not nearby in the way a neighbor is nearby. Nearby in the way that gravity, warmth, energy, and a functioning communication link with 300 million problem solvers on a habitable planet were always within reach. When the Mir space station suffered a collision with a Progress cargo vessel in June 1997, puncturing the Spectra module and causing rapid depressurization, the crew had minutes to seal the breach. But they were not alone. Ground controllers in Moscow were monitoring telemetry in near real time, diagnosing the extent of the damage and relaying guidance on which systems to isolate and which to preserve. The crew sealed the module, stabilized the station, and continued operations. The crisis lasted hours. The support from Earth was continuous. When the Hubble Space Telescope launched with a flawed mirror in 1990, a repair mission was planned, a shuttle was sent, astronauts physically replaced the optics, and one of the most important scientific instruments ever built went from a national embarrassment to a national triumph. When the Mars rovers, Spirit and Opportunity, encountered software glitches and stuck wheels millions of miles from Earth, engineers uploaded patches, rerouted navigation algorithms, and kept both machines operating years beyond their designed lifetimes. Each of these stories is told as a triumph of human ingenuity, and each one also rests on a foundation that is so taken for granted it has become invisible. The foundation is proximity. Not proximity in human terms, proximity in mission terms. Close enough to talk, close enough to think, close enough to intervene, close enough to bring someone home. Every single link in that chain breaks when you cross the boundary we have already described. And it does not break gently. It breaks in a way that makes every other link break faster. Start with propulsion, because everything else follows from how long the journey takes. If the journey could be made in days, most of the other problems would shrink to manageable size. Radiation exposure would be brief. Life support demands would be limited. Communication delays would be bounded. System degradation would be minimal. The reason interstellar travel is not simply a harder version of interplanetary travel is that no known or seriously proposed propulsion technology can compress the travel time to anything close to a human-scale duration for a crewed vessel. We covered the broad landscape of propulsion options earlier. What matters now is the consequence of those limitations when they are placed inside a real mission architecture. Consider what happens when you accept that the journey will take decades at minimum and centuries under more realistic projections. A crewed mission to Mars, using current or near-future propulsion, would take roughly 7 to 9 months in each direction. The crew spends somewhere between 1 and 3 years away from Earth in total. That is a long mission by current standards, but it fits within the operational lifetime of existing spacecraft systems. Environmental control systems on the International Space Station have operated for over 2 decades with continuous resupply and maintenance from Earth. A Mars crew would carry supplies and spares for a bounded duration, and while the engineering is demanding, the timescale is within the range of systems that have been tested. Now, changed the timescale. A journey to the nearest star, even at an optimistic 1% of light speed, takes over 400 years. At 5% of light speed, which no current technology can achieve for a crewed vessel, it takes roughly 87 years. At 10%, which remains firmly theoretical for anything larger than a gram-scale chip, it takes about 43 years. These are the most favorable numbers available. They assume propulsion breakthroughs that do not yet exist. And they produce mission durations that transform every downstream system from a solvable engineering problem into an open question with no tested answer. There is another dimension to the propulsion problem that is almost never discussed in popular accounts of interstellar travel, and it roughly doubles the severity of every number just described: the deceleration problem. Every discussion of reaching Alpha Centauri in 43 years or 87 years assumes not just that you can accelerate to the required velocity, but that you can also stop when you arrive. Breakthrough Starshot, the most ambitious interstellar concept ever funded, was explicitly designed as a flyby mission. Its gram-scale probes would scream past Alpha Centauri at 20% of the speed of light, capturing what data they could in a few hours of close approach, unable to slow down, unable to enter orbit, unable to linger. For a robotic chip, this is a tolerable compromise. For a human crew, it is meaningless. You cannot colonize a star system you are passing through at 60,000 kilometers per second. You cannot study a planet you are next to for an afternoon. You cannot disembark from a vessel that never stops. A human interstellar mission must decelerate. And deceleration, in the merciless arithmetic of rocketry, is not simply the reverse of acceleration. It is a second acceleration, applied in the opposite direction, requiring its own fuel, its own energy, and its own time. The Tsiolkovsky rocket equation, the fundamental relationship governing how much propellant a spacecraft needs, shows that carrying fuel to decelerate at the destination means that fuel must itself be accelerated during the outbound phase. The fuel needed to stop requires fuel to move. That fuel requires more fuel to move. The exponential nature of the equation means that the total propellant requirement does not double when you add deceleration. It compounds. For a vessel traveling at 10% of light speed that must slow to orbital velocities at the destination, the total energy requirement, including deceleration, can be 4 to 10 times greater than the energy for acceleration alone, depending on the propulsion method and the mass ratio of the ship. This single factor transforms the already impossible energy budget described earlier into something that does not have a name in engineering, because no engineer has ever faced a requirement this far beyond the available resources. Some proposals attempt to sidestep the deceleration problem by using the destination star's own light for braking, deploying a light sail to catch photons from Alpha Centauri and slow the vessel as it approaches. The physics is valid in principle, but the engineering requirements are extreme. The sail would need to be enormous, far larger than anything used for acceleration, and deployed at precisely the right moment during approach. The braking maneuver would take years or decades, adding substantially to the total mission duration. And it only works for star systems bright enough to provide sufficient photon pressure, which excludes the majority of stars in the galaxy. The deceleration problem is not a footnote. It is a multiplier applied to every other challenge in this story. Every kilogram of shielding, every liter of water, every spare part, every gram of food must not only be accelerated to interstellar speed, but also decelerated at the far end. The mass spiral we are about to encounter is not a single spiral. It is a double spiral, and the second loop is larger than the first. 43 years is the lower bound, the most optimistic, credible scenario. In those 43 years, every mechanical component on the spacecraft must function. Every seal must hold. Every pump must cycle. Every electrical connection must remain intact. Not most of them. All of them, or at least enough of them, to sustain the critical systems that keep the crew alive and the ship on course. There is no resupply. There is no maintenance depot. There is no second ship following behind with spare parts. Whatever the crew brings at departure is all they will ever have. The engineering term for this is logistics closure. In a closed logistics environment, every consumable has a fixed quantity and every system has a finite number of spare components. The mission duration determines how many spares are needed, how much redundancy must be built in, and how much total mass must be launched. As mission duration increases, the mass budget for spares and consumables grows. But mass is the most expensive commodity in space travel. Every additional kilogram requires more propellant to accelerate, more structural strength to support, and more energy to move. This is the mass spiral. Longer missions need more supplies. More supplies mean more mass. More mass means more propulsion. More propulsion means more fuel. More fuel means more mass. The equation does not converge toward a solution. It diverges. At interstellar timescales, the mass requirements for a crewed vessel with full logistics closure exceed anything that could be launched from Earth using any plausible method. This is not a funding problem. It is not a political will problem. It is a physics problem. The energy needed to accelerate the mass, needed to sustain the crew for the duration dictated by the speed achievable with the propulsion available, creates a loop that feeds on itself until the numbers become absurd. Some proposals attempt to escape this loop by making the ship self-sustaining, grow food on board, recycle all water, regenerate all atmosphere, manufacture spare parts from raw materials carried in bulk. This is the closed ecological life support concept, and it is worth examining in detail because its failure modes reveal something important about the nature of the interstellar challenge. The most ambitious closed ecological experiment ever attempted on Earth was Biosphere 2, a 3.14-acre sealed facility in Arizona that housed 8 crew members from September 1991 to September 1993. The facility was designed to be completely self-sustaining, recycling air, water, and food through integrated biological systems. It failed in multiple critical ways. Oxygen levels dropped to the equivalent of an elevation of roughly 13,000 feet, low enough to impair cognitive function. Carbon dioxide fluctuated unpredictably. Crop yields were insufficient. Pollinating insects died off. Pest species thrived. Condensation patterns caused structural corrosion that had not been anticipated. The social dynamics among the 8 crew members deteriorated to the point of conflict that affected mission operations. Biosphere 2 was not in space. It was in Arizona. It sat on solid ground with stable gravity, surrounded by breathable atmosphere on the other side of its walls, with electrical power supplied from the external grid, and with the certain knowledge that, if anything went catastrophically wrong, the crew could simply open a door and walk out. It still failed. The lesson is not that closed ecological systems are impossible. Research has continued, and smaller-scale systems have shown improved results. The lesson is that biological life support is not a solved problem. It is not even close to a solved problem at the scale and duration required for interstellar travel. A closed life support system that must function reliably for 43 years, the minimum optimistic transit time, with no external inputs and no margin for error, demands a level of ecological engineering that exceeds anything ever demonstrated by a factor of roughly 20 in duration alone. And 43 years assumes propulsion that does not exist. Under more realistic speed assumptions, the required duration stretches into centuries, and the reliability requirements become, in the precise engineering sense of the word, unprecedented. Now, layer on communication, because the failure of communication does not just isolate the crew emotionally. It removes the single most powerful asset that has saved every space mission that has ever gone wrong: the ability to consult Earth. At the distance of the Moon, communication delay is about 1.3 seconds. Conversations are awkward but functional. At Mars distance, the delay ranges from roughly 4 minutes to 24 minutes, depending on orbital positions. This is manageable for planned operations, but devastating for emergencies. Rovers on Mars are designed with significant autonomy precisely because waiting 40 minutes for a round-trip instruction is too slow for real-time navigation. At the distance of Jupiter, the delay stretches to roughly 35 to 52 minutes one way. At Saturn, over an hour. At the current distance of Voyager 1, a round-trip signal takes nearly 2 full days. But all of these are still inside the solar system. All of these still allow communication, even if delayed. An engineer on Earth can still send a software patch. A scientist can still analyze telemetry and recommend a course of action. The connection is slow, but it exists. At Alpha Centauri, a one-way signal takes 4 years and 4 months to arrive. A question asked today would not receive an answer until roughly 2035 if asked right now. By the time the answer arrived, the situation that prompted the question would be years in the past. The crew would have already solved the problem, failed to solve it, or died from it long before Earth even knew it had occurred. This is not a communication delay. It is communication severance. The practical difference between a 4-year signal delay and no communication at all is negligible for any time-critical scenario. A medical emergency, a structural failure, a navigation error, a mechanical breakdown, a fire, a collision with interstellar debris, any event that requires a response faster than years is an event that the crew must handle entirely on their own, with whatever knowledge, tools, and ingenuity they have on board, with no possibility of assistance from the 300 million engineers, scientists, physicians, and problem solvers on Earth who have historically been the real margin of survival for every space mission ever flown. The loss of that margin is not incremental, it is total, and it applies to every emergency, every ambiguity, every technical question, every medical diagnosis, and every judgment call for the entire duration of the mission. Radiation is the next compounding factor, and it is one that cannot be solved by cleverness alone because it is embedded in the environment itself. Within the solar system, the sun's magnetic field creates a protective bubble called the heliosphere. The heliosphere is not a perfect shield. Solar particle events, the bursts of high-energy protons released during solar flares and coronal mass ejections, can deliver dangerous doses of radiation to astronauts beyond low Earth orbit. But the heliosphere does attenuate the background flux of galactic cosmic rays, the high-energy particles that originate from supernovae and other extreme astrophysical events outside the solar system. Galactic cosmic rays are a different category of threat from solar radiation. They include heavy ions, nuclei of elements like iron and carbon, traveling at significant fractions of the speed of light. These particles carry enormous kinetic energy relative to their size. When they strike biological tissue, they do not simply pass through or cause superficial damage. They carve tracks of destruction through cells, breaking DNA strands, killing cells outright, or worse, damaging them in ways that lead to cancer, degenerative diseases, and central nervous system impairment years or decades later. Research published in Frontiers in Nuclear Medicine and elsewhere has documented the specific health risks. Prolonged exposure to galactic cosmic radiation is associated with elevated cancer risk, cataracts, cardiovascular disease, immune system suppression, impaired wound healing, and cognitive decline, including deficits in memory, executive function, and anxiety regulation. A study in Scientific Reports using simulated galactic cosmic ray exposure found persistent cognitive dysfunction in animal models, including reduced dendritic complexity and altered spine morphology in prefrontal cortical neurons. These are not speculative risks. They are measured outcomes from controlled experiments using the types and energies of particles found in the galactic cosmic ray environment. The numbers make the timescale problem concrete. NASA's current career exposure limit for astronauts is approximately 600 millisieverts, a threshold set to keep the estimated increase in lifetime cancer mortality risk below 3%. Beyond the heliosphere, the unshielded galactic cosmic ray dose rate is estimated at roughly 600 to 700 millisieverts per year or higher, based on measurements from the radiation assessment detector aboard the Curiosity rover during its transit to Mars, which recorded approximately 1.84 millisieverts per day. That figure was measured inside the heliosphere with some spacecraft shielding. Beyond the Sun's protective bubble, the flux increases further. At that rate, an astronaut on an interstellar vessel would reach NASA's entire career exposure limit in under a year. A 43-year journey, the absolute minimum under the most optimistic propulsion assumptions, would deliver a cumulative dose exceeding 40 times the career limit. The biological consequences of that level of exposure are not fully characterized because no human being has ever experienced it, but extrapolations from animal studies and from the epidemiology of radiation workers and atomic bomb survivors indicate sharply elevated risks of solid cancers, leukemia, cardiovascular disease, and neurodegenerative conditions. The central nervous system effects are particularly concerning for a crew that must maintain cognitive function, judgment, and technical competence across decades. Research has shown that even moderate galactic cosmic ray exposure produces measurable declines in spatial memory, executive function, and fear extinction in animal models. A crew suffering progressive cognitive impairment while simultaneously managing the most complex engineering systems ever built, with no external support and no possibility of medical evacuation, faces a failure mode that is not mechanical but biological. The crew itself degrades. Inside the heliosphere, these particles are partially deflected. Beyond it, they are not. An interstellar vessel would spend the vast majority of its journey outside the heliosphere, exposed to the full, unattenuated flux of galactic cosmic rays for decades or centuries. Shielding is the obvious response, but shielding against galactic cosmic rays is not analogous to shielding against solar radiation or the radiation encountered in low Earth orbit. High-energy heavy ions interact with shielding material in complex ways. When a galactic cosmic ray strikes a metal hull, it can produce a shower of secondary particles, including neutrons, that may be more biologically damaging than the original particle. This is called secondary radiation production, and it means that simply adding more metal to the hull can, paradoxically, increase the radiation dose inside the spacecraft rather than reduce it. Researchers have explored alternative shielding materials, including polyethylene and water, which produce fewer secondary neutrons due to their high hydrogen content. Active magnetic shielding, generating an artificial magnetosphere around the spacecraft, has been proposed but never demonstrated at the scale required. Each approach adds mass, complexity, and points of failure to a mission that already strains the limits of what can be launched, accelerated, and sustained. And none of them, in current or foreseeable form, can reduce the galactic cosmic ray dose to levels that are considered safe for multi-decade human exposure. The radiation problem does not sit beside the propulsion problem, it sits on top of it. Inadequate propulsion means longer transit times. Longer transit times mean more radiation exposure. More radiation exposure means more shielding, which means more mass, which makes the propulsion problem worse. This is the compounding effect. Every shortfall feeds every other shortfall. There is another physical hazard that occupies the same compounding space as radiation, and it is one that does not exist at all within the solar system at the speeds we currently travel: the interstellar medium. The space between stars is not perfectly empty. It contains a thin but measurable distribution of gas, primarily hydrogen and dust, tiny particles of silicate, carbon, and ice. The density is extraordinarily low by terrestrial standards, roughly 1 atom per cubic centimeter in the local interstellar medium near our solar system. At the speeds of current spacecraft, these particles are negligible. Voyager 1, traveling at 17 kilometers per second, encounters them as a faint whisper of resistance, detectable by its instruments but irrelevant to its structure. At interstellar velocities, the situation changes categorically. At 10% of the speed of light, roughly 30,000 kilometers per second, the kinetic energy of any impact scales with the square of velocity. A dust grain, the mass of a grain of fine sand, roughly 1 milligram, striking a spacecraft at 10% of light speed, carries kinetic energy equivalent to approximately 450 megajoules. That is roughly the energy released by 100 kilograms of TNT. A single grain of dust, invisible to the naked eye, hitting with the force of a substantial bomb. And the interstellar medium contains not just occasional grains, but a continuous distribution of particles across a range of sizes. Over a journey of 4.37 light-years, the spacecraft's forward-facing surface would encounter billions of hydrogen atoms per second and a statistically significant number of larger dust particles. At higher velocities, this problem worsens dramatically. At 20% of light speed, the energy per impact quadruples. The cumulative effect is not just erosion of the hull surface, although that is a real concern over decades of flight. It is the possibility of catastrophic structural failure from a single impact with a particle large enough to penetrate shielding. Designing a forward shield capable of absorbing these impacts adds yet more mass to the vessel, feeds back into the propulsion and deceleration spirals, and introduces another system that must function perfectly for the entire duration of the journey. The interstellar medium is not hostile in the way that radiation is hostile, silently degrading biology from within. It is hostile in the way that a minefield is hostile, presenting a low but non-zero probability of instantaneous catastrophic damage at every moment of the journey, for decades, with no possibility of repair if the worst case occurs. System degradation is the next strand in this compounding web, and it may be the most insidious because it operates silently. Machines wear out, seals degrade, lubricants evaporate. Electronic components suffer cumulative damage from radiation and thermal cycling. Mechanical systems fatigue from repeated stress cycles. Biological systems, including human bodies, accumulate damage from microgravity, radiation, and the metabolic consequences of a confined environment. All of these processes accelerate in space. On Earth, machines are maintained by a civilization of factories, supply chains, trained technicians, and raw material extraction systems. On the International Space Station, critical systems are replaced regularly with components launched from Earth. A pump that fails on the ISS can be replaced by an identical unit manufactured on Earth, tested and delivered within months. On an interstellar vessel, a pump that fails must be repaired with on-board resources or replaced by a spare carried from departure. When the spares run out, the crew must fabricate replacements from whatever materials are available. This requires manufacturing capability, which requires machine tools, which require power, which requires fuel or energy generation, which itself degrades over time. The Voyager spacecraft illustrate this reality with painful clarity. Their radioisotope thermoelectric generators, which convert the heat of decaying plutonium-238 into electricity, have lost so much power over the past 49 years that only 2 scientific instruments remain operational on Voyager. One, as of 2026. Engineers have had to make agonizing choices about which systems to shut down and which to keep running. The spacecraft's hydrazine thrusters are clogging from fuel residue accumulated over decades. There are no backup thruster systems remaining. Every remaining system is the last of its kind aboard the spacecraft, with no redundancy and no replacement. And Voyager is a machine that weighs less than a ton, carries no crew, and has no life support systems to maintain. Now imagine a vessel carrying hundreds of human beings, with atmospheric recycling, water purification, food production, medical facilities, waste processing, navigation systems, propulsion maintenance, structural integrity monitoring, and the 1,000 other systems required to keep a small civilization alive inside a metal shell hurtling through interstellar vacuum at enormous speed. Every one of those systems is degrading. Every one of them is aging. Every one of them is accumulating the fatigue and wear that will eventually cause failure. The question is not whether failures will occur. The question is whether the crew can repair them faster than they accumulate. And over decades or centuries, in a closed system with finite resources and no external support, the answer is not guaranteed. Psychological endurance is a factor that engineers sometimes treat as secondary to the physical challenges, but researchers who study long-duration spaceflight have increasingly placed it at the center of mission viability. The longest continuous stay in space by a single individual is approximately 437 days, set by Russian cosmonaut Valery Polyakov aboard the Mir space station. Studies of Polyakov and other long-duration crew members have documented the psychological toll of confinement, isolation, and distance from Earth. Sleep disruption, interpersonal conflict, motivational decline, and altered cognitive performance are consistently reported even on missions measured in months, with a crew that can see Earth from the window and talk to family members with only a few seconds of delay. An interstellar crew would face confinement not for months, but for decades. They would have no window view of home, no real-time conversation with anyone on Earth, no prospect of return within their lifetime under most mission architectures. They would live and die inside the ship, and if the mission spans multiple generations, their children and grandchildren would inherit a situation they never chose, in a vessel they cannot leave, traveling toward a destination they will never reach, because it is their descendants, not them, who will arrive. The psychological literature on isolation, confinement, and involuntary commitment offers no precedent for a scenario of this duration and severity. The closest analogues, Antarctic winter-over expeditions, submarine deployments, and prison populations, all involve durations of months to years, not decades or centuries, and all include the foundational knowledge that the confinement will end. An interstellar crew would have no such knowledge. For most of the journey, there would be nothing outside but void. No milestones, no landmarks, no approaching destination visible to the eye. Just the slow tick of years inside a vessel that constitutes the entirety of their world. Every factor discussed in this section interacts with every other factor. This is not a list of independent problems. It is a web of interdependent failures, each one pulling the others tighter. Propulsion limits dictate transit time. Transit time dictates radiation exposure, system degradation, life support duration, and psychological load. Radiation exposure degrades both crew health and electronic systems, increasing the rate of failures that the crew must repair. System degradation consumes spare parts and manufacturing capacity, reducing the margin available for future failures. Life support complexity increases the number of systems that can fail and the consequences of each failure. Psychological deterioration reduces the crew's capacity to manage all of the above. Communication severance removes the external support that has historically compensated for each of these weaknesses on every previous mission. The interstellar medium adds a continuous probabilistic threat of impact damage that grows more severe at higher speeds, the same higher speeds needed to reduce transit time and the compounding effects of every other factor. Deceleration requirements roughly double or quadruple the energy budget and the mass that must be accelerated, feeding back into every link of the chain. and mass requirements for shielding, spares, supplies, and redundancy feed back into the propulsion problem, demanding more energy, more fuel, and more engineering to move a vessel that grows heavier with every additional safeguard. This is the compounding collapse. It is not one wall. It is a series of walls, each one built from the rubble of the last, each one taller because the previous one could not be climbed. The reason this matters is not that any individual problem is unsolvable in principle. Given unlimited time, resources, and luck, humanity might solve any one of them. The reason it matters is that an interstellar mission requires all of them to be solved simultaneously, for the same vessel, sustained across the same timescale, with no possibility of external intervention if any solution fails. That simultaneity requirement is what separates the interstellar challenge from anything humanity has attempted before. It is not the difficulty of any single element. It is the demand that every element must work, all at once, for longer than anything has ever worked before, with no safety net beneath it. What follows will examine what this means in structural terms, not just what each system requires, but what the total mission architecture looks like when you attempt to assemble all of these requirements into a single coherent design. And why that assembly may reveal a threshold that is not defined by any single engineering limit, but by the combined weight of all of them pressing down at once. Every spacecraft ever built was designed to come home. That sentence sounds obvious. It sounds like it should not need to be said. But it contains something fundamental that disappears so completely in discussions of interstellar travel that its absence goes unnoticed. Like a foundation removed from beneath a building, so slowly that no one sees the walls beginning to lean. The Mercury capsules were designed to splash down in the Atlantic. The Gemini capsules carried retro rockets for re-entry. The Apollo command modules were engineered around a specific thermal profile for atmospheric return at lunar velocities. The space shuttle was, by definition, a reusable vehicle whose entire architecture revolved around the return trip. Even the robotic missions that were never intended to come back physically were designed to return something. Data, telemetry, images, science. Every probe that has ever been launched carried with it the assumption that the information it gathered would reach Earth, would be received by human beings, and would be integrated into the body of knowledge that justified the mission in the first place. Return is not a feature of spaceflight. It is the premise. It is the invisible architecture on which everything else is built. And it is the first thing that disappears when a mission crosses the boundary between the solar system and the interstellar void. Within the solar system, return is difficult but real. A crew on the Moon can abort and reach Earth in approximately 3 days. A crew on Mars can, in principle, launch from the Martian surface and return to Earth in a window of roughly 2 years, limited by orbital mechanics rather than absolute impossibility. Even at the outer planets, robotic missions carry the implicit return of information. Voyager 1's signal, faint and slow as it is, still reaches Earth. The Deep Space Network still receives it. Engineers still respond. The conversation continues. Beyond the solar system, return ceases to exist in any meaningful operational sense. A crewed vessel traveling to Alpha Centauri at 5% of the speed of light, an achievement that no propulsion technology can currently deliver, would require roughly 87 years for the outbound journey alone. A round trip, assuming the vessel could decelerate, spend time at the destination, and accelerate back, would span well over 2 centuries. The crew that departed would not return. Their children would not return. Their grandchildren might, if the ship survived, if the systems held, if the population remained viable, if the knowledge required to operate, the vessel persisted across multiple generations of people who had never seen Earth and had no personal connection to it. This is not hyperbole. This is arithmetic applied to the distances involved and the speeds achievable. And the implications of that arithmetic radiate outward into every aspect of mission design, mission psychology, and mission survival in ways that most discussions of interstellar travel never fully confront. The loss of return is not simply a psychological blow. It is the removal of a structural element that has been load-bearing in every space mission ever flown. To see what this means concretely, consider 3 moments from the history of spaceflight, each one a crisis that was survived because of an architecture that cannot exist beyond the solar system. In April 1970, an oxygen tank aboard Apollo 13 exploded roughly 200,000 miles from Earth, crippling the command module's power, water, and life support. The crew survived because mission controllers in Houston could communicate with them in near real time, because a team of hundreds of engineers on Earth could design improvised solutions using the exact inventory of materials known to be aboard the spacecraft, and because the Moon's gravity provided a free return trajectory that brought the crew home without requiring the crippled service module to fire its main engine. The round-trip communication delay was roughly 2.6 seconds. The total time from explosion to splashdown was less than 4 days. Every element of the rescue depended on proximity to Earth. In May 2013, the International Space Station developed an ammonia leak in one of its external cooling loops, a failure that, if unchecked, could have forced shutdown of critical systems. Ground controllers detected the leak in telemetry, diagnosed the probable source, and directed an emergency spacewalk within 48 hours to replace the suspect pump controller and stop the leak. The entire response was coordinated from the ground, using diagnostic tools, engineering databases, and specialist expertise that existed on Earth and were transmitted to the station in seconds. In October 2018, a Soyuz rocket carrying 2 crew members to the ISS suffered a booster separation failure during ascent, triggering an automatic abort that separated the crew capsule and brought both astronauts back to Earth within minutes. The abort system worked because the crew was still close enough to the surface for a ballistic re-entry to be survivable. Each of these events ended in survival because the mission was inside the solar system, close to Earth, connected to ground support, and within the reach of abort, rescue, or real-time intervention. Now map each scenario onto an interstellar mission. An Apollo 13-style failure aboard a vessel 4 light-years from Earth would produce no response from mission control for nearly 9 years, round trip. No improvised solution from Houston. No engineering team working through the night. The crew would have roughly the same amount of time Apollo 13's crew had, hours to days, to save themselves using only what they carried. An ISS-style cooling system failure diagnosed from the ground would be undiagnosable from the ground because the telemetry would not arrive for years. A Soyuz-style launch abort is irrelevant because there is no surface to return to, no atmosphere to re-enter, no planet beneath the spacecraft at all. Just void in every direction for light years. The rescue architecture that has saved human lives in space is not a portable system. It is an ecosystem rooted in the proximity of Earth, and it has no equivalent beyond the solar system. The no-rescue threshold is not a single dramatic line in space. It is the point at which every emergency becomes a local emergency, solvable only by those present, with no external input, no second opinion, no backup team, and no abort. That point arrives the moment the communication delay exceeds the response time required to address a critical failure, and it never reverses for the remainder of the journey. Consider what a mission without return actually requires. Start with the most basic question: who goes? On every previous human spaceflight, the crew was selected, trained, launched, and expected to come back. They volunteered, knowing the risks, but also knowing the timeline. Months, a year, perhaps 3 years for a future Mars mission. The sacrifice was bounded. The absence from family and home was temporary. An interstellar crew faces a categorically different proposition: They are not leaving home for a period. They are leaving home permanently. They will never see Earth again. They will never breathe unrecycled air. They will never walk under an open sky. Every relationship they have with anyone not on the vessel ends at departure, not because communication is cut off instantly, but because the growing delay renders conversation meaningless within a few years, and the people they left behind will age and die while the crew is still in transit. This is not a deployment, it is an exile. And it is an exile that extends to every subsequent generation born aboard the ship, none of whom will have chosen it. The ethical dimensions of this are significant, but the practical dimensions are what concern us here. A crew that has volunteered for permanent departure must also be a crew that can sustain itself biologically, socially, psychologically, and technically for the duration of the journey. That requirement creates a minimum viable population, a concept borrowed from conservation biology that refers to the smallest number of individuals needed to maintain genetic diversity and avoid the health consequences of inbreeding over multiple generations. Estimates vary depending on assumptions about reproductive patterns and genetic management, but most studies place the minimum viable population for a multi-generational human settlement at somewhere between 160 and several thousand individuals. The lower estimates assume carefully managed breeding programs. The higher estimates assume more natural reproductive patterns and a margin of safety against catastrophic population loss from disease, accident, or social disruption. Even the lower bound of 160 people implies a vessel of extraordinary size. Each person requires living space, personal space, workspace, medical care, food production area, water recycling capacity, atmospheric processing, waste management, exercise facilities to counteract the physiological effects of microgravity or artificial gravity, and recreation to sustain psychological health over decades. Multiply each of those requirements by 160 or more, and the vessel becomes not a ship, but a small city. A self-contained, self-sustaining, mobile habitat that must function as a complete civilization with no external inputs for a century or more. The mass of such a vessel, even with aggressive miniaturization and efficiency, would be enormous. The energy required to accelerate it to interstellar speeds would be correspondingly vast. And every additional kilogram of structure, supply, and shielding feeds back into the compounding propulsion spiral we have already seen. The generation ship concept is the only interstellar mission architecture that does not require a fundamental breakthrough in physics. It accepts the speed limitations of plausible propulsion systems and compensates by extending the mission duration across human lifetimes. In principle, it works. A vessel traveling at even a modest fraction of a percent of light speed could eventually reach another star system, arriving after centuries or millennia. The passengers who arrive would be the distant descendants of the passengers who departed. The concept has been explored extensively in science fiction and occasionally in technical literature. What is less commonly explored is what the concept actually demands in terms of sustained operational capability. A generation ship must maintain atmospheric composition within breathable limits for centuries. Not approximately, precisely. The partial pressures of oxygen, nitrogen, and carbon dioxide must remain within narrow physiological bounds continuously. If oxygen production falters because a crop fails, or an algae bioreactor malfunctions, or a chemical scrubber degrades, the entire population is at risk. There is no opening a window. There is no backup atmosphere. The ship is a sealed vessel surrounded by vacuum, and the atmosphere inside it is the only atmosphere that exists for everyone aboard. Water recycling must operate at near perfect efficiency because the total water budget is fixed at departure. Every molecule of water lost to leakage, chemical binding, or system inefficiency is a molecule permanently removed from the supply. Current water recycling systems on the International Space Station, after recent upgrades, recover approximately 98% of wastewater. That is impressive for a station resupplied regularly from Earth. For a closed system operating over centuries, even 98% recovery means losing 2% of the water supply with each full cycle through the system. Even with improvements, any recovery rate below 100% compounds into a deficit that eventually becomes critical. The food production system must generate sufficient calories, protein, fats, vitamins, and minerals for the entire population, every day, for centuries. Agricultural systems on Earth depend on open cycles of sunlight, rain, soil nutrients, pollinators, and pest control that are regulated by an entire planetary biosphere. Reproducing this inside a sealed vessel requires artificial lighting, hydroponic or aeroponic growth systems, nutrient management, pollination by hand or by managed insect populations, and disease and pest control without the ecological buffers that stabilize terrestrial agriculture. Any sustained failure in food production, whether from crop disease, equipment breakdown, contamination, or loss of seed stock, threatens the survival of the population. And agricultural systems are among the most biologically complex and failure-prone systems that could be installed aboard a spacecraft. But the engineering challenges, formidable as they are, may not be the deepest problem with the generation ship concept. The deepest problem may be continuity. Not mechanical continuity, human continuity. A generation ship requires not just a surviving population, but a functioning society. One that maintains the technical knowledge needed to operate and repair every critical system on the vessel. One that preserves the institutional memory of why the mission exists, where it is going, and what must be done upon arrival. One that sustains motivation, discipline, cooperation, and purpose across generations of people who were born inside the ship, have never known any other existence, and have no experiential connection to the world that launched the mission or the world that is its destination. No human institution has ever demonstrated this kind of continuity. Consider what has happened on Earth over timescales comparable to an interstellar journey. 300 years ago, the dominant global powers were different from those today. The scientific understanding of the universe was radically different. The languages spoken in major capitals have shifted. Entire systems of governance have risen and collapsed. Religions have split, reformed, and transformed. The technologies in daily use bear no resemblance to those of 3 centuries ago. And all of this happened on a planet with billions of people, vast resources, open skies, and the constant stimulation of a diverse and changing environment. Now compress that same timescale into a sealed vessel with a few hundred people. No horizon, no weather, no seasons, no new arrivals, no departure of old members except through death, no external events to mark the passage of time, and no tangible evidence that the destination exists beyond what the navigation computer reports. The social dynamics of such a community are without precedent. The historical record offers instructive, if imperfect, analogues. Pitcairn Island, settled in 1790 by the Bounty mutineers and a small group of Tahitian men and women, is among the most isolated permanent human communities ever established. The initial population was 28. Within a decade, violence, alcoholism, and internal conflict had killed most of the adult men. The community survived only because it was eventually discovered by passing ships and received external contact, supplies, and governance support from Britain. Without that external intervention, the settlement was on a trajectory toward extinction. The population today, sustained by supply ships and communication with the outside world, hovers around 50. It has never been self-sufficient. It has never been truly isolated. And it has never maintained continuity of purpose across its generations in any structured sense. The early American utopian communities of the 18th and 19th centuries offer another lens. Groups like the Shakers, the Harmonists, and the Oneida community were founded with intense shared purpose, strict governance structures, and deep ideological commitment. Most lasted fewer than 3 generations. The Shakers, who prohibited reproduction and relied on conversion for population growth, effectively went extinct as a functioning community. The Harmonists dissolved after their founder's death. The Oneida community abandoned its communal structure within 30 years. Each of these groups had access to arable land, breathable air, clean water, external trade, and the option of departure for dissatisfied members. They still could not maintain institutional coherence across a handful of generations. A generation ship offers none of those advantages and removes the single most powerful release valve for social tension, the ability to leave. Studies of isolated communities on Earth, from island populations to polar research stations to submarine crews, consistently show that prolonged isolation and confinement produce predictable patterns of social fragmentation, authority challenges, clique formation, motivational collapse, and interpersonal conflict. These studies involve durations of months to a few years, with populations that chose their confinement and know it will end. A generation ship population would face confinement measured in lifetimes, with no prospect of its ending for anyone currently alive. The governance problem alone is staggering. Who leads the ship? How is leadership selected? What happens when a faction disagrees with the mission plan? On Earth, political disagreements can lead to separation. Groups that disagree can migrate, secede, or simply avoid each other. On a generation ship, there is nowhere to go. Every disagreement must be resolved within the same sealed environment, using the same limited resources, among the same small population. The historical record of small, closed communities attempting to maintain cooperative governance over extended periods is not encouraging. Mutinies, schisms, power struggles, and authoritarian takeovers are recurring patterns in isolated groups, and these patterns emerge even when the stakes are relatively low and the duration is relatively short. On a generation ship where the stakes are existential and the duration is centuries, the pressures driving these dynamics would be amplified beyond any historical precedent. Knowledge preservation presents a related challenge. The crew that departs Earth would include specialists trained in every system aboard the vessel, but those specialists will age and die during the journey. Their knowledge must be transferred to the next generation, who must transfer it to the next, and so on for the duration of the mission. This requires an educational infrastructure capable of producing highly trained engineers, physicians, biologists, navigators, and systems operators from a population of a few hundred, generation after generation, without access to universities, research institutions, professional communities, or the broader intellectual ecosystem that supports technical education on Earth. If any critical area of expertise is lost, if a generation fails to produce a qualified specialist in atmospheric chemistry or reactor maintenance or medical surgery, the ship does not simply experience an inconvenience. It experiences a potentially fatal knowledge gap that cannot be filled from outside. There is another dimension to the interstellar threshold that receives less attention than propulsion or life support, but may be equally decisive. Energy. Not energy in the abstract, motivational sense, but energy in the physical, thermodynamic sense. Every system on the vessel requires power. Lighting, heating, cooling, atmospheric circulation, water pumping, food production, communication, navigation, computing, medical equipment, manufacturing, and propulsion maintenance all draw from the same energy budget. And that budget must last for the entire journey. Nuclear fission reactors are the most energy-dense technology currently available for space applications. A fission reactor could, in principle, power a vessel for decades. But fission reactors require fuel, typically enriched uranium or plutonium. The fuel is consumed as the reactor operates. A reactor designed to run for a century would require either an enormous initial fuel load or the ability to reprocess spent fuel on board, a technology that adds complexity, mass, and additional points of failure. Fission reactors also produce waste heat that must be radiated into space, requiring large radiator surfaces that are vulnerable to micrometeorite damage and thermal fatigue over long periods. Fusion reactors, if they could be made to work reliably, would offer better energy density and cleaner operation. But as noted earlier, controlled fusion has not yet been achieved for sustained power generation on Earth, where engineers have access to unlimited cooling, maintenance infrastructure, and the ability to rebuild failed components from scratch. Achieving fusion aboard a spacecraft and maintaining it for decades without interruption is a challenge that sits on the far side of a problem we have not yet solved on the near side. Radioisotope thermoelectric generators, the technology that powers Voyager, are reliable but produce very small amounts of power relative to their mass. They are suitable for robotic probes but wholly inadequate for a crewed vessel with the energy demands described above. Solar power, the backbone of the International Space Station, diminishes with the square of the distance from the Sun. At the orbit of Mars, solar panels produce roughly 43% of the power they produce at Earth's distance. At the orbit of Jupiter, roughly 3.7%. Beyond the solar system, solar power is effectively zero. The ship must carry its own energy source, and that source must last for the duration of the journey. The energy cliff is not a metaphor. It is a thermodynamic reality that constrains everything else the mission can do. All of these factors converge on a single concept that defines the interstellar threshold more sharply than any individual engineering challenge. The concept is mission autonomy. Within the solar system, no human mission has ever been fully autonomous. Every crewed flight has operated within a support architecture that includes ground control, resupply capability, abort options, medical consultation, software updates, and the psychological anchor of a home that is reachable within a bounded time frame. Even robotic missions deep in the outer solar system depend on commands from Earth, diagnostic support from engineering teams, and the knowledge infrastructure of an entire civilization to interpret their data and guide their operations. An interstellar mission has none of this. It is, from the moment it passes beyond communication range, a closed system in every sense. Closed materially, closed energetically, closed informationally, closed socially. Every resource it will ever have is aboard at departure. Every problem it will ever face must be solved from within. Every loss, whether of equipment, of knowledge, of population, or of social cohesion, is permanent and irreplaceable. This level of autonomy has never been attempted. It has never been tested. It has no analog in human experience. The closest parallel is perhaps the settlement of remote oceanic islands by Polynesian navigators thousands of years ago. But even those voyages, extraordinary as they were, involved journeys of weeks or months between islands that shared the same planetary environment, the same atmosphere, the same gravitational field, and the same biological compatibility with human life. The interstellar void shares none of these characteristics. It is radiation-saturated vacuum at a temperature just above absolute zero, offering nothing that sustains human life and everything that threatens it. What emerges from this analysis is not a list of problems to be solved. It is a recognition that the interstellar challenge is not a problem at all in the engineering sense. A problem has a solution space. It has parameters that can be varied, constraints that can be relaxed, and objectives that can be traded off against each other. The interstellar challenge is a condition. It is a set of simultaneously binding constraints that cannot be relaxed because they arise from the fundamental physics of distance, energy, time, and human biology. You cannot reduce the distance. You cannot ignore the radiation. You cannot pause the aging of systems and people. You cannot conjure resources that were not loaded at departure. You cannot accelerate communication beyond the speed of light. You cannot compress the journey below the time dictated by available propulsion without inventing propulsion that does not exist. And you cannot remove any one of these constraints without leaving all the others in place, each one sufficient on its own to threaten mission survival and devastating in combination. This is the threshold that no previous mission was designed to cross. Not because engineers were unaware of it, but because every previous mission, including the most ambitious ones ever imagined and funded, was designed for a domain where the threshold does not apply. The solar system is that domain. It is the region of space where communication works, where return is possible, where resupply is conceivable, where the sun provides energy and magnetic shielding, and where the distances, vast as they are by human standards, remain within the operational range of systems that can be built, tested, and maintained by a civilization on the other end of a functioning radio link. Beyond the solar system, every one of those conditions vanishes, not gradually, not one at a time, all of them, together, past a boundary that is not a wall in space but a threshold in capability. The question that remains, the one we must now confront directly, is what this threshold means. Not what it means for engineering, not what it means for mission planning. What it means for the species that stands on one side of it, looking outward, wondering whether the stars that fill the night sky are destinations it will ever reach, or lights it will only ever watch. From a distance it cannot cross. The answer to that question requires one final shift in perspective. Away from the engineering, away from the numbers, away from the systems and the shielding and the life support diagrams, toward the recognition that the solar system may not be what we have always assumed it is. Not a cradle to be outgrown, not a nursery to be left behind, but a domain whose boundaries may already mark the outer edge of what human presence can sustain, not because the universe is hostile, but because the margin between where we can survive and where we cannot may be narrower than anyone wanted to believe. There is a moment in every long journey where the traveler stops looking forward and turns around, not because they have lost their nerve, not because the destination has become less real, but because the distance already covered has changed what the place they left looks like. The view from far away reveals proportions that were invisible up close. Mountains that seemed like barriers from the valley floor become small wrinkles in a landscape that extends in every direction without end. The village that felt like the whole world becomes a speck, then a smudge, then a memory held together by nothing but the knowledge that it is still there, somewhere behind, growing smaller with every step. Humanity has not yet taken the step that would trigger this moment. We have not left. We are still inside the solar system, standing at the edge of our village, looking outward at a darkness that stretches in every direction for distances that our nervous systems were never designed to process. But we have built instruments that can see farther than our feet can carry us. And what those instruments reveal, when combined with everything described so far in this story, is a picture that is both grander and more constrained than the one most people carry in their imaginations. The solar system, measured to the outer boundary of the Oort Cloud, spans over 3 light-years in diameter. That number has appeared several times already, but it is worth pausing on one final time, because it contains a paradox that sits at the heart of this entire story. Over 3 light-years is enormous by any human standard. It is so large that the fastest object humanity has ever launched will not cross it for another 30,000 years. It contains the Sun, 8 planets, hundreds of moons, dwarf planets, millions of asteroids, billions of comets, and enough scientific mystery to occupy every researcher on Earth for centuries without exhausting the questions. It is a domain so vast and so rich that calling it a starting point feels almost ungrateful, like standing in a cathedral and complaining about the size of the door. And yet, measured against the distances that separate stars, even 3 light-years is vanishingly small. Alpha Centauri, the nearest star system, is 4.37 light-years away. The gap between the outer edge of the solar system and the nearest neighboring star is roughly 2.8 light-years, a void nearly twice the distance from the Sun to the solar system's own outer boundary. And Alpha Centauri is the closest star. The vast majority of stars in the Milky Way are hundreds, thousands, or tens of thousands of light-years away. The galaxy itself spans roughly 100,000 light-years from edge to edge. The solar system, placed on that scale, is not a launch pad. It is a grain of sand on a beach that stretches beyond the horizon in every direction. This is not a new observation. Astronomers have understood the scale of interstellar distances for centuries. What is newer, and what the preceding sections of this story have tried to make vivid, is the recognition that the scale is not merely a logistical inconvenience. It is a qualitative barrier. The difference between traveling within the solar system and traveling beyond it is not the difference between a short drive and a long drive. It is the difference between driving on a road with fuel stations, rest stops, hospitals, phone service, and a home to return to, and driving off the edge of the continent into open ocean with no map, no radio, no rescue, no destination in sight, and a vehicle that was never tested for salt water. The infrastructure of survival that makes human space exploration possible, communication with Earth, the possibility of resupply, the option of return, the protective environment of the heliosphere, the energy of the Sun, the gravitational architecture that allows calculated trajectories, all of it ends at the solar system's edge. What lies beyond is not a continuation of what lies within. It is the absence of everything that made the journey inside possible. If you plot distance from the Sun on one axis and cumulative mission difficulty on the other, the curve does not rise smoothly. Within the solar system, difficulty increases with distance, but the increase is gradual enough that each increment can be managed with improvements in technology, mission planning, and experience. Going from low Earth orbit to the Moon was hard, but the increase in difficulty over suborbital flight was surmountable. Going from the Moon to Mars is harder still, but the increase over lunar missions, while significant, is addressable with technology that either exists or is within plausible reach. Going from Mars to the outer planets adds communication delay, transit time, and radiation exposure, but robotic missions have demonstrated that these challenges can be met for unmanned spacecraft. The curve is rising, but it is rising at a rate that human engineering has historically been able to match. Then, the curve reaches the heliopause. And somewhere between the heliopause and the inner edge of the Oort Cloud, the curve bends. It does not just steepen, it changes character entirely. The increase in difficulty per unit of additional distance becomes exponential rather than linear. Communication delay does not just grow longer, it passes a threshold beyond which real-time interaction becomes impossible. Radiation exposure does not just increase, it enters a regime where cumulative dose exceeds any demonstrated shielding capacity over the required mission duration. System degradation does not just accelerate, it enters timescales beyond any tested operational lifetime for any crewed system. Life support does not just become harder, it requires complete ecological closure at durations and scales never demonstrated. And return does not just become more difficult, it becomes physically impossible within the lifetime of any crew member aboard. Each of these transitions happens in the same region of the curve. They do not arrive one at a time, spaced out across a gentle gradient. They arrive together, in a cluster, at the boundary where the solar system's protective architecture gives way to the unmediated hostility of interstellar space. This clustering is not a coincidence. It reflects the fact that the solar system is not just a collection of planets orbiting a star. It is an integrated environment, a system in the deepest sense, where the sun's gravity, magnetic field, energy output, and the orbital mechanics of its planetary bodies create the conditions that make human activity in space possible. When you leave that system, you do not just lose the sun's light. You lose the entire infrastructure that the sun's presence creates, and you lose it all at once. This is the insight that changes the shape of the conversation. The question is not whether humanity can build a faster rocket. The question is not whether we can invent better shielding, or close the life support loop, or develop fusion propulsion, or solve any one of the individual engineering challenges described in this story. Any one of them might be solved, given enough time and resources. The question is whether all of them can be solved simultaneously, integrated into a single mission architecture, and sustained across the timescales that interstellar distances impose without the support of the civilization that solved them. Because that is what an interstellar mission requires. It requires the crew to carry not just supplies and equipment, but the functional equivalent of a civilization. The knowledge, the skills, the social structures, the manufacturing capability, the educational systems, the medical expertise, the governance frameworks, and the collective will to maintain all of these across generations inside a sealed vessel with no external input, no reinforcement, no correction, and no rescue. No human community has ever demonstrated this capability, not because no community has tried, but because the conditions that would require it have never existed. Every human community in history has existed within an environment that provides at least some external support, whether from the natural world, from neighboring communities, from trade networks, or from the accumulated infrastructure of previous generations. An interstellar vessel would be the first human community to exist in total isolation from everything external, the first to depend entirely on what it carries within itself, the first to have no margin for error that cannot be filled from within. There is a temptation, when confronting this reality, to invoke future technology, to say that we do not yet know what breakthroughs await. That the history of science is a history of things once thought impossible becoming routine. That the people who said humans would never fly were proved wrong. And the people who said we would never reach the moon were proved wrong. And the people who say we will never reach the stars will be proved wrong in turn. This argument is emotionally powerful and historically grounded. It is also structurally incomplete. The breakthroughs it points to, powered flight, space flight, lunar landing, were achievements that overcame specific engineering barriers within an environment that remained fundamentally supportive. The Wright brothers did not need to invent a new atmosphere. The Apollo engineers did not need to create a new sun. Each breakthrough operated within the physical environment that Earth and the solar system provided, exploiting resources and conditions that already existed. The interstellar challenge is different in kind. It does not ask humanity to do something difficult within a supportive environment. It asks humanity to sustain itself within an environment that provides nothing for durations that exceed any tested system, at distances that preclude any assistance, while simultaneously solving every unsolved problem in long-duration life support, radiation protection, closed-loop ecology, multi-generational governance, and propulsion engineering. The analogy to previous breakthroughs is not apt. Previous breakthroughs were keys that opened doors. The interstellar challenge is not a locked door. It is the absence of a floor. This does not mean that nothing will ever cross the gap. Robotic probes can tolerate what human beings cannot. A machine does not need air, water, food, sleep, social interaction, medical care, or hope. A machine can travel in silence for millennia without suffering. A machine can absorb radiation doses that would kill a human crew within months. A machine can operate at temperatures and in vacuum conditions that are instantly lethal to biological life. Voyager 1 is the proof. It has been flying for nearly 50 years, returning data from the edge of interstellar space, enduring conditions that no human being could survive for an hour. It will continue to drift through the galaxy for millions of years after its power supply fails and its transmitter goes silent, a monument to what machines can do that humans cannot. But a robotic flyby is not human exploration, it is remote observation. The data that Voyager returns is received and interpreted by human beings on Earth, but Voyager itself experiences nothing. It does not know where it is. It does not understand what it has found. It is an extension of human curiosity, not a replacement for human presence. The question this story is asking is not whether humanity can send an object beyond the solar system. We already have. The question is whether humanity can send itself. Whether human beings, in their biological fragility, their social complexity, their psychological needs, and their dependence on a web of systems that must function simultaneously and continuously, can survive the crossing from one stellar domain to another. And the honest assessment, based on everything currently known about the physics, the engineering, the biology, and the sociology of such a mission, is that we do not know. What we do know is that the list of unsolved requirements is long, that the requirements are interdependent, that no subset of solutions is sufficient without all the others, and that the combined difficulty of the full set exceeds anything humanity has previously attempted by a margin that is not incremental but categorical. There is a counter-argument to this conclusion that deserves honest engagement, because it is the strongest objection a thoughtful person might raise, and dismissing it would weaken rather than strengthen the case being made here. The counter-argument is artificial intelligence, not the AI of science fiction, not a sentient robot with human emotions and a desire to explore, but the real and rapidly advancing capability of machine intelligence to manage complexity, maintain systems, make decisions, and preserve knowledge across timescales that no biological crew could sustain. If the limiting factor of interstellar travel is ultimately the fragility, mortality, and social instability of human beings, then the argument goes like this. Remove the human beings from the transit phase. Send an AI-managed vessel carrying frozen embryos, or digitized human genomes, or a complete archive of human knowledge and culture, or even a seed civilization designed to be activated upon arrival. Let the machine do what machines do better than humans. Endure. Let it cross the void in silence, maintaining systems, correcting errors, navigating hazards, operating on timescales that would drive any conscious crew to despair, and arrive at the destination with the cargo intact and the mission fulfilled. This is not a fantasy. It is a plausible extension of technologies that are advancing rapidly in the 2020s. Artificial intelligence systems already pilot spacecraft, manage life support aboard the ISS, diagnose system anomalies, and process data from deep space probes with minimal human intervention. Extrapolating those capabilities across decades of further development, it is not unreasonable to imagine a machine intelligence capable of managing an interstellar vessel for centuries. The question this counter-argument raises is real and important, but it also reveals, with great clarity, the specific nature of the boundary this story has been describing. Because an AI-managed vessel carrying frozen biological material across interstellar space is not human exploration, it is human replication. The distinction matters. Human exploration, in every historical instance, has meant human beings experiencing the journey, making decisions during transit, adapting to conditions as they are encountered, and arriving as a functioning community capable of acting on what they find. An AI cargo ship arriving at Alpha Centauri with a genetic archive is an extraordinary technological achievement if it could be built. But the humans it might someday produce at the destination would not be explorers who crossed the void. They would be a new population created at the far end, with no memory of the journey, no continuity of experience with the civilization that launched the mission, and no personal connection to Earth beyond what the archive contains. This is not a trivial distinction. It goes to the heart of what people mean when they say humanity will reach the stars. They do not mean that human DNA will reach the stars. They mean that human beings, conscious, aware, experiencing the crossing and remembering it, will reach the stars. And that specific aspiration, the one that animates the dream of interstellar travel in every conversation and every story, is the one that the compounding challenges described here may foreclose. The AI counterargument does not dissolve the boundary. It redraws it with greater precision. Machines may cross, information may cross, genetic material may, under extraordinary circumstances, cross. But the experience of crossing, the human experience of living through the journey from one star to another and arriving on the other side as a society, may be the specific thing the threshold does not permit. Something bearing humanity's mark may leave. But humanity, in the full sense of the word, may not. There is something important that this story is not saying, and it is worth making explicit because the line between realism and despair is worth drawing clearly. This story is not saying that interstellar travel is physically impossible. The laws of physics do not prohibit it. There is no equation that says a human being cannot travel from one star to another. What the laws of physics do is specify the costs, the energy required, the time involved, the shielding demanded, the mass implications. And those costs, when calculated honestly and combined into a single mission profile, produce a total that exceeds any demonstrated or plausibly near-term human capability. The gap between what is physically permitted and what is practically achievable is where this story lives. The physics allows it. The engineering, as currently understood, does not deliver it. The question is whether that gap will close. It might. It might close through breakthroughs in propulsion that are not yet imagined, through materials science that enables radiation shielding without prohibitive mass, through artificial intelligence that can manage the complexity of a self-sustaining vessel better than any human crew, through biological engineering that extends human lifespans or radiation tolerance, through social innovations in governance and education that enable multi-generational continuity in closed communities. Any of these might happen. None is guaranteed. And the interstellar threshold requires not one of them, but all of them, simultaneously integrated into a coherent whole and proven reliable at durations and scales for which no test environment exists. There is a deeper current running beneath the engineering arguments, and it surfaces now because this is the section where it belongs. The assumption that humanity will expand beyond the solar system is not merely a technical prediction, it is a psychological need. It is tied to something fundamental in how human beings understand their significance in the universe. If we can reach the stars, then the story of our species is a story of infinite potential, of growth without limit, of a future that extends across the galaxy and perhaps beyond. The universe becomes a canvas. Our role is to fill it. If we cannot reach the stars, if the solar system is not a cradle but a boundary, the story changes. Not into a tragedy, but into something more constrained than the version most people grew up believing. The solar system is not a prison. It is an enormously rich domain, and human exploration within it has barely begun. The moons of Jupiter and Saturn alone present scientific questions that could occupy generations. The asteroid belt contains resources that dwarf anything available on Earth's surface. Mars may harbor evidence of past life. Venus may offer atmospheric chemistry that reshapes our understanding of planetary evolution. The outer solar system is a wilderness of ice worlds, radiation belts, and magnetic environments that we have only glimpsed from flyby distances. There is enough within the Sun's domain to sustain human curiosity, human ambition, and human expansion for centuries. but it has a boundary. And that boundary may be real in a way that is not simply a challenge to be overcome with sufficient determination, but a reflection of the physical relationship between human biology, human engineering, and the environment that lies beyond the last reach of our star's influence. The most unsettling realization is not that the stars are far away. Everyone knows the stars are far away. The realization is that the first truly great boundary of human expansion may not be between galaxies, not between star clusters, not even between neighboring stellar systems. It may be right here, at the edge of the Oort Cloud, at the threshold where the sun's gravitational influence gives way to the galactic tide, at the line where the last tenuous connection to the system that birthed us, that warmed us, that shielded us, that gave us a place to stand and a signal to follow home, fades into the background radiation of interstellar space. The boundary is not dramatic. There is no wall. There is no gate. There is no sign that reads, "You are now leaving the solar system." There is only a gradual thinning of everything that made the journey possible. A weakening of gravity. A fading of the solar wind. A dimming of the sun from a burning disk to a bright point, to one star among many, to a faint speck indistinguishable from the rest of the sky. And somewhere in that thinning, the systems that sustain human life cross a threshold from strained to insufficient. Not all at once, not with a single dramatic failure, but through the slow accumulation of deficits that cannot be corrected because the distance has grown too large, the delay too long, the isolation too complete, and the resources too finite to absorb one more loss. Voyager 1 is approaching one light day from Earth. By late 2026, a signal sent from Mission Control at the Jet Propulsion Laboratory in Pasadena will take a full 24 hours to reach the spacecraft. The response, if one comes, will take another 24 hours to return. A 2-day round trip for a conversation that on Earth takes place at the speed of thought. The spacecraft carries a golden record. Pressed into its surface are sounds and images selected to represent the diversity of life and culture on Earth. Greetings in 55 languages. Music from Bach to Chuck Berry. The sound of a human heartbeat. The cry of a newborn child. Photographs of mountains, oceans, cities, and faces. Diagrams showing our position in the galaxy and the structure of our DNA. The record was designed to be found. It was designed for the possibility that somewhere, sometime, another intelligence might encounter this small machine drifting through the dark, decode its message, and understand that a species once existed on a pale blue world orbiting a yellow star, a species that wondered whether it was alone and hoped desperately that it was not. Voyager will never deliver that message to anyone. The distances between stars are so vast that the probability of another civilization intercepting a spacecraft the size of a small car, traveling on a trajectory that will not pass near any known star for 40,000 years, is effectively zero. The golden record is not a letter that will reach its recipient. It is a message in a bottle thrown into an ocean that has no far shore. It will drift through the galaxy for millions of years, long after its transmitter has gone silent, long after its systems have shut down, long after the civilization that launched it has either flourished beyond recognition or vanished entirely. It will carry the sounds of Earth through a silence that nothing will break. And that silence is not a temporary condition. It is the nature of the medium. Space is not empty in the metaphorical sense of waiting to be filled. It is empty in the physical sense of containing nothing that human life can use, touch, breathe, or draw comfort from. The void between stars is not a gap to be crossed. It is an environment, the dominant environment of the universe, and it is one in which human beings cannot survive without carrying everything they need with them, sustaining it indefinitely, and solving every problem that arises without help from anyone or anything outside their vessel. Voyager 1 does not know any of this. It does not know that it is farther from home than anything humanity has ever built. It does not know that its power is fading, that its instruments are shutting down one by one, that the engineers who keep it alive are running out of options. It does not know that it is approaching a milestone that will make its loneliness measurable in light days. It carries no crew, it feels no cold, it experiences no isolation. It simply flies, as it has flown for nearly 50 years on a trajectory set by a gravity assist at Saturn in 1980, moving at 38,000 miles per hour through a darkness that will never end. It is the most distant expression of human ambition in the history of the species. And it is a reminder, quiet but absolute, that ambition and capability are not the same thing. We dreamed of the stars. We reached for them with everything we had. And the farthest we have gotten, after 5 decades of flight at speeds no human body has ever experienced aboard any crewed vehicle, is 1 light day, a single light day. The nearest star is roughly 1,600 light days away. The gap between where we are and where the dream lives is not a gap that willpower can close. It is a gap measured in physics, in energy, in time, in the fragility of human bodies and the limits of human machines. And the most terrifying possibility is not that the gap is large. It is that the gap may be permanent. Not because the universe forbids the crossing, but because the crossing demands a perfection of engineering, endurance, and civilizational continuity that our species may never be able to assemble all at once, in a single vessel, sustained across the centuries required to reach the other side. The solar system is not a prison, it is a home. A vast, rich, extraordinary home, filled with wonders we have not yet visited and mysteries we have not yet solved. But it may be the only home we will ever have. And the stars, brilliant and countless, burning in the dark beyond the Oort Cloud, may remain forever what they have always been. Lights in the distance, beautiful, unreachable, and silent.